Today we're going to talk about how enzymes can influence a reaction's activation energy. But first let's review the idea that enzymes make biochemical reactions go faster. And in order to do that, they use a bunch of different catalytic strategies. Now there are lots of different catalytic strategies that enzymes use, but a couple of the key ones are acid-base catalysis, where enzymes use their acidic or basic properties to make reactions go faster by helping out with proton transfer. There's also covalent catalysis, where enzymes covalently bind a reacting molecule to help with electron transfer. There's electrostatic catalysis, where enzymes use charged molecules or metal ions to stabilize big positive or negative charges. And we also have proximity and orientation effects, where enzymes make collisions between reacting molecules happen a little more often. So what effect do these catalytic strategies actually have on a reaction? Well, let's look at a sample reaction where we're having molecule A being converted to molecule B. Now, we can look at the process of this reaction using something called a reaction coordinate diagram. And here, we'll plot the energy state of our molecules against the progress of the reaction. So essentially, using this graph, we'll follow the energy level of molecule A as it's converted to molecule B. Remember that a molecule's energy level is related to its stability, and something that is a lower energy state is more stable, and for something to transform to a more unstable form, it needs an input of energy to get there. So looking at this graph, you'll notice that the energy of molecule A will rise up pretty high, and then drop all the way down to the energy of molecule B. And we can actually define a couple of values from this graph. The transition state of a reaction, which is represented by this double dagger symbol, is the highest energy point on the path from A to B, and it's where you'll find the most instability throughout the entire reaction. Now the difference between the energy level where we start and the top of our graph at our transition state is what we call the delta G double dagger, or the free energy of activation. And this is the amount of energy that A needs to have in order to break the reaction barrier to ultimately get to point B. You'll also notice that there is a difference in energy between point A and point B, and we call this the standard free energy change for the entire reaction, and it represents the net change in energy levels between our reactant and our product, and it's also the energy that is released into the environment once the reaction is over. Reactions you typically look at will have their products at a lower energy state than their reactants, since that makes the reaction spontaneous. Now, it's important to recognize that it is the free energy of activation energy value, which is the difference between point A and the transition state, that usually determines how quickly a reaction will go. And usually this energy value is much higher than the free energy change for the reaction, which is why enzymes speed up a reaction by lowering a reaction's activation energy. Now, I want to quickly point out that you may see delta G double dagger written out as EA in some textbooks, and you may see the standard free energy change for the reaction written out as E reaction. And I'm just letting you know that you might see both sets of terms used from time to time. Now, let's look at an analogy to get a closer look at how this all works. And let's say there's a giant hill that you're trying to climb, and it's a pretty steep hill that goes up really high, but you need to get to the other side of the hill. Now, this would be a pretty scary thing on its own, since you would need to go all the way up and then all the way down the mountain to get to the finish line. But if I were to give you a shovel, then now you could dig your way through the mountain and not have to climb up so high. In this example, the shovel represents an enzyme, and the hill represents the activation energy barrier that prevents you from getting to start to finish. By using the shovel, you're able to lower the height of the hill you have to climb. But in both cases, it's important to recognize that you still started and finished at the same points. So let's go back to our example from before with our reaction coordinate diagram. But now, let's say that the reaction has a catalyst. So with the catalyst, the activation energy barrier that molecule A has to overcome in order to get to point B is much smaller. And this will mean that your reaction will have a transition state with a much lower energy, meaning that it's more stable with the enzyme, and also that the reaction as a whole will have a much lower activation energy. Now, it's really important to recognize that, like our example where you're trying to climb the hill, the enzyme will not be changing the starting and ending points of the reaction. It doesn't change molecule A or molecule B. Your starting and ending points are always the same, and the only thing that changes is the path that you take to get from A to B. Now, since our starting and ending points aren't changing, it follows that the enzymes are not used up when they catalyze a reaction, and there is no permanent change to the enzyme following a reaction. So what did we learn? Well, first we learned that enzymes work by lowering the free energy of activation of a reaction. making it much easier for the reactants to transition and form products. And we also learned that the free energy of the reaction doesn't really change when you use an enzyme and when you don't. Second, we learned that despite the change in pathway to get from A to B, the reactants and products do not change when using an enzyme versus when not using an enzyme. And finally, we learned that enzymes are not consumed when they catalyze a reaction, and the same enzyme can catalyze reactions over and over again.